I just want to get you guys kind of excited about the sun and the neat things we're doing to study the sun, the observations, the theory, and the modeling. This was my original title. I decided to expand things a bit, although we'll see how much I expand. And this is the new title, Magnetic Explosions on the Sun. All right. So the first, no, all right, it's, there it goes. Maybe just a delay, I guess. It's up there now. All right. So, all right, please, I want this to be informal. I guess it is pretty informal, but let's maintain that informality. I don't want it to be a lecture. Let's make it a discussion. So, you know, if I say something you don't understand, or if there's something you don't understand because I haven't said anything at all, just please interrupt, ask questions. I really want you guys to come away with, learning something about the sun and how the sun works, not just how it looks. All right. So most of the real interesting phenomena on the sun, and in fact, many of the very interesting phenomena throughout the whole universe involve magnetic explosions. There are magnetic fields everywhere. These fields, if they're stressed, they contain stored magnetic energy. That energy can be released to do many things. It can heat the gas to very high temperatures. It can accelerate the gas to very high velocities. It can create highly energetic particles, relativistic particles, all sorts of really cool things. This is happening from magnetic explosions. And, all right, I will talk about two types of explosions on the sun, covering the two ends of the spectrum of explosion size. On the small end, we have things called nanoflares. On the large end, things called coronal mass ejections. So I'll try. Good, it's showing up here. It'll probably be a delay. All right. While we're waiting, here we are. So these explosions take place in the solar corona. The corona is the outer atmosphere of the sun. It's above the so-called surface. Now, of course, the sun doesn't have a hard surface. It's a gas, but it's relatively very high density gas. Up above it, the gas is rarefied, and that's the solar corona. That's where all the action takes place. All right. This is an eclipse photograph from the eclipse, what was it, 7 years ago that went across North America. Here's the corona. In an eclipse, the moon blocks the bright face of the sun. Many people will say you can only see the corona during total solar eclipses. Well, that's true if you're talking about visible light from between 4,000 to 7,000 angstroms. Right? That's the light that our eyes are sensitive to. In that light, the corona is really faint compared to the solar disk. It's 1,000,000 times fainter. So if the disk is there and you don't block it out, you're just going to be blinded by all that light. You won't have any chance of seeing the diffuse corona.
Sorry, audio is not fully functioning. Yeah, just,
okay.
Just had to.
Thank you. I guess I have to keep moving the mouse around here. All right, and this is how the corona looks. It's got a lot of structure to it. That structure comes from the magnetic field, which I'm arguing is the most important thing. And the word corona, it's a Latin word meaning crown. So when people many years ago saw these eclipses, they thought, wow, this is really cool. The sun has kind of a crown on its head. So that's the origin of the word corona. All right, so this is invisible light. But we look at the sun in all different kinds of light, the different parts of the spectrum. Visible light is just a tiny sliver of the full spectrum. We have radio waves and microwaves and ultraviolet and X-ray and gamma rays. And if you look at the sun in those types of light, it turns out the corona is bright compared to the disk of the sun. The disk is faint, so you don't have to block the disk. You don't need a moon there to allow you to see the corona. You can just see it, whenever you want, as long as you're up in space, because most of this light, like this movie here, is from observations in the extreme ultraviolet at about 171 angstroms. Okay, so this ultraviolet light gets absorbed by the Earth's atmosphere. So if you want to see the sun, you got to get above the atmosphere. So we have orbiting spacecraft, orbiting observatories that look at the sun in all different kinds of light besides visible light. Okay. Fine. And then this sequence happens to have been taken by a mission called the Solar Dynamics Observatory. And it shows when it's playing, it shows the rotation of the sun. It takes 27 days for the sun to execute one complete rotation. Okay, wow, that's just finding new movies on my computer that are not part of the presentation. All right, so this is ultraviolet light, and this tells us that the corona is hot because this emission at 171 angstroms, that's produced by highly ionized iron that's had many of its electrons stripped away. And the only way to have that kind of a condition is with very high temperatures. So the fact that we see the sun in ultraviolet and in X-ray and other high energy emissions shows us that the corona is very hot. In fact, it's about 1,000 times hotter than the solar surface. And the surface we call the photosphere. So the surface has a temperature of about 5,000 degrees, which is awfully hot, right? But the corona is several million degrees, 1,000 times hotter. So the big question is, why is the corona so hot? That's been one of the real fundamental questions in astrophysics for many, many decades. And we have more or less found the answer. There are many, I wouldn't call them just details. There are many things to be sorted out, but we basically understand why the corona of the sun and other stars is so hot. And that's what I want to talk about, at least in the first part of this talk. All right, so why is it hot? Well, here's kind of a clue. This shows the sun as seen in soft X-ray light. So this is 1 to 10 angstroms, even shorter wavelengths than the ultraviolet. Again, from orbiting observatories above the Earth's atmosphere. And here we have one image of the sun each year for the 11-year solar cycle. There's a solar cycle. You've probably heard about the sunspot cycle. It's roughly 11 years. Well, it's not just sunspots that become more and less common during the solar cycle, but many other things change, such as the X-ray emission. So you see here, you have a lot of X-ray emission. These especially bright areas are called solar active regions. During the maximum of the cycle, you have many such active regions, and then they get less and less common. Then you're back here in the back where there are no active regions. This is the minimum of the cycle. Then 5.5 years or so later, we come back around to the maximum again. All right, so there's a variability. Now let me show you corresponding maps of the magnetic field on the surface of the sun. The X-rays were coming from the corona. This now is a map of the magnetic field on the solar surface. We call these photospheric magnetograms. So where you see white and black, that's where there are very strong magnetic fields. And magnetic fields have direction. So white means the strong fields are pointed out of the sun. Black means they're pointed into the sun. And sort of neutral gray areas, that's where the fields are weak. Now, I hope I'll be able to toggle back and forth, but maybe I don't need to. But you can tell there's a very good correspondence between the bright X-ray emission and the areas of strong magnetic field. Right. So that's the clue. The magnetic field must be playing a role in coronal heating. And really, it's all about the magnetic field. So here is an image of a solar active region up close. You see a lot of these beautiful arching type structures. We call those coronal loops. These loops trace out the magnetic field. So here, you've all seen, I presume, demonstrations at school or at museums. You sprinkle iron filings on the table, you put a bar magnet down there, and it organizes the iron filings into this nice pattern with these arching things here. Well, the magnetic field is just that, it's a field. There are invisible lines of force. We call those magnetic field lines. And on the bottom here, this is a sketch of the magnetic field lines, or the lines of force associated with that bar magnet. And you can see the filings are organized along those magnetic field lines. Similarly, in the corona, we have the same situation. Now, the corona, as I've emphasized, is very hot. That means it's a plasma. A plasma is a type of gas. Normally, gas means neutral. All the particles in this room, the nitrogen and the oxygen and all that, they're neutral. Each atom has all of its electrons that put it in its fundamental state. equal numbers of electrons and protons, so it's neutral. But when you have a hot gas and all these atoms are banging around off of each other, the electrons get knocked off. And so you have charged particles. You have the positively charged nucleus and the negative electrons moving around, and that's called a plasma. It's a gas made up of charged particles. And these plasmas interact very closely with the magnetic field. In fact, the field and the plasma are frozen together. So plasma can easily flow along the magnetic field lines, but not across them. So I like to think of an abacus, right? There's a wire and the beads. The beads can flow up and down along the field lines. Those are the particles, but they can't move across the field lines. They can't move across the wire. If the particles are strong, they can bend the wire, but they can't actually move across the wire. We have that same situation with plasmas and magnetic fields. Okay. And so these arching loop structures, those are plasma structures. Those are guided by the magnetic field. So they're tracers of the magnetic field. All right. And then move ahead here. All right. So the real story begins at the solar surface, the photosphere. The photosphere is undergoing what's called turbulent convection. It's in a constant state of motion. There are these upwellings and downdrafts. This is a close-up of the photosphere. The area there is about the size of the Earth, roughly. And what's happening is you have hot gas rising up to the surface from below, rising up buoyantly, then it spreads out, and then it cools and it sinks back down. So you have these rotational cells. And each of these little blobby things is one of these convection cells. It's exactly what happens in the kitchen if you have a pot of oil on the stove, a heated pot of oil. It's not boiling. That's different. With boiling, there's a change of state. You take liquid water, you turn it into gaseous water. But with the oil, it's always in the liquid form. But at the bottom, it's very hot, so it buoyantly rises up, gets to the surface, cools off, goes back down again. Cyclical pattern. These are the cycles happening in photospheric convection. And the magnetic field is rooted in this ever-changing plasma. The magnetic field pokes up out of the solar surface into the corona, and these white areas here, these are the places where intense magnetic field is sticking out of the photosphere up into the corona, and it goes up and it spreads out and it fills the corona. And these places where the coronal field is rooted in the photosphere, we call those foot points typically. So you can see that these foot points are being moved around in chaotic ways. And that's causing the magnetic field up above, the coronal field, to become tangled and twisted, meaning it becomes stressed. And energy is being pumped into that magnetic field. So here we go. This is a nice image of the corona. Down below it, we have the photosphere, like from this patch here. So photospheric convection is moving those foot points of the coronal field lines, making them tangled and twisted. This is a cartoon sketch, obviously. So here are the individual strands. They're tangled and twisted. Not following what I'm showing you. Anyway, so tangled and twisted here. So the boundaries between the strands are places where the magnetic field suddenly changes direction. And there's a famous law, Ampere's law. It's one of the famous four Maxwell's equations that says whenever you have a magnetic field changing direction abruptly over a short distance, then you have electric currents. And these are called current sheets. So between all these tangled and twisted strands, we have electric current sheets, and that's where all the action takes place. That's where we get these things called nanoflares. All right. This is from a talk that I gave at the American Geophysical Union. It's something called the Parker Lecture. If you're interested, there's a QR code. You could check out my talk. But we have the photosphere tangling the coronal field. It becomes stressed. The field then reaches a breaking point, and it releases that magnetic energy, and it heats the plasma. And I should point out that magnetic fields are a lot like rubber bands, really. That's a good analogy. Imagine you have a rubber band, and you stretch it and stretch it. You're putting stress in it, it snaps all of a sudden, and then it flies back and hits your hand, so it's converted that rubber energy into kinetic energy of the motion and the pain energy in your hand. So magnetic fields do the same thing. They're like rubber bands. All right. So I think that's all I wanted to say about this. Yeah, checking my time here. All right. So how exactly do the fields break? I brought up the rubber band analogy. Well, the way they break is through a process called magnetic reconnection. This is an amazingly important, a fundamental process at the heart of many phenomena all throughout the solar system. I mean, it's really basic. And unlike the rubber band analogy, where the rubber band actually breaks, that you have one band that breaks into two parts, magnetic fields can't do that. There's something called the divergence-free condition. Magnetic fields can't break. The line of force can't suddenly end. It always has to continue. But you can have two field lines coming together, as in this video. We have one field line that's directed from right to left. That's the blue one at the top. And then below it, one directed from left to right. When these come together, they touch and they switch partners. They like pinch off. And so now you have two new field lines that are going to move away to the left and right. Okay, that's the essence of magnetic reconnection. Incredibly important. When it does this, it converts magnetic energy into all these other forms, including heat. All right, here is a simulation. The thing before was quite obviously a cartoon. This is a simulation. So I have two magnetic flux tubes, orthogonal. In the back, I have a vertical flux tube, and in the foreground, I have a horizontal flux tube. Come on. There it is. Here it is here. So here's from the simulation. I'm going to keep moving this cursor so it won't turn off, hopefully. In the simulation, I show only the vertical flux tube in the back. I don't show the horizontal flux tube. It would be too complicated. But when reconnection happens, the vertical and horizontal convert into diagonal flux tubes. All right. So next is a movie. This is a very cool movie. Come back. Please play. Why are you not playing? Bugger. There. Okay, there it is. Now play. That's not playing. That's a shame. It looks really cool in the movie. All right, well, let's move ahead. All right. Well, that's actually really quite an old computer simulation. We have more sophisticated simulations now. Here are the results from one of them. These are called magneto-hydrodynamic simulations. Magneto, because the magnetic field's involved. Hydrodynamic, that refers to the plasma. So it's this interplay between the field and the plasma that produces so much neat stuff. All right. So on the left is going to be a cartoon showing the arching magnetic loops. This vertical plane cuts through them. And then on the right, this is from the simulation, a map of the emission within that plane. Emission that's due to all of these nanoflares going off. So here's something about nanoflares. So nanoflares, nano means 1/1 billionth. So a nanoflare is 1,000,000,000 times smaller than a regular flare. So sounds pretty wimpy, right? But each of these nanoflares is the equivalent of a 50 megaton hydrogen bomb, the largest bomb ever detonated here on Earth. That's one nanoflare. And we have roughly 1,000,000 or so of them going off every second across the sun. So collectively, they're very powerful. All right. So now I hope that I'll be able to show you a movie here. Playing. That's the bad news. I have lots of very cool movies. And they aren't playing. I set this so they play automatically when I switch slides. Yeah, I wanted to show you lots of really nifty things. No, it's not even showing on my screen for some reason. I ran through this, before coming, and everything was working just fine. But back is fine, and forward is fine.
That the resolution of this machine isn't compatible with the projector.
Possible, but I would suspect that it's more connected.
But some of the movies worked, at least temporarily,
Yeah.
didn't they? It's the different movie formats have MP4
It's this device. It's just a brick.
It looks like just a hub.
because I don't have a
The USB.
USB.
Okay.
Well, no, I don't have an HDMI. I have USB. If I could connect with
that's an
USB.
HDMI.
Yeah, if you had a USB, I think that would. I've never had a problem with that.
The only thing else I can think of doing, and it would take a while, would be to move it onto the room machine.
We only have about 20 minutes left. All right, so yeah, all right. So we'll skip over some of the really slick stuff. How about this? No movie here. All right. So you understand, I think, the basic story. Nanoflares heat the corona. The corona emits in all these emissions, ultraviolet and X-ray. And ultraviolet and X-ray emissions, they have a huge impact on the Earth's upper atmosphere, the ionosphere and the thermosphere. And they produce space weather. Okay, and not just the Earth's upper atmosphere, but the upper atmospheres of exoplanets orbiting other stars. So what kind of effects do we have? Well, for example, when the emission goes up, there's more energy being put into the Earth's atmosphere, the ionosphere and the thermosphere. It heats up, it expands, and that means at any given altitude, the altitude where some satellite is orbiting, the density goes up at that altitude because of this expansion of the atmosphere. So that means more drag on the satellite. And that can cause big problems because, we don't want our satellites to crash into space debris. And so there are a lot of maneuvers that go on all the time to move satellites out of the way of debris. But if you don't really know what's happening with your satellite, how its orbit is degrading all of a sudden because of this effect, then that causes a real problem for collision avoidance operations. Also, radio signals get affected. Propagation of radio signals. On the cartoon on the right, if it shows up, I indicate these things called plasma bubbles or irregularities in the Earth's ionosphere. So radio waves, instead of traveling in straight lines, they get deflected in all sorts of crazy ways. So that screws up things like communication systems, obviously, but also navigation systems and even surveillance systems. And there's another effect which has to do with how ionized the atmosphere becomes. More X-ray and ultraviolet light causes more ionization of the ionosphere, and that affects the altitude where we intentionally want to bounce signals, right? You've shortwave radio operators, you can talk to people around the world because radio waves are bouncing off layers in the ionosphere. Well, we use that also for over-the-horizon radar. So in order to do that effectively, you need to know what your bouncing altitude is. Where is this mirror? But with the solar radiation changing, the mirror is moving up and down, and that can cause real problems. All right. So now I mentioned other planets as well. The X-ray and UV light from the parent stars causes the atmospheres of the exoplanets to gradually escape. So many planets lose their atmospheres altogether. And this is happening on Mars too. Mars used to have a much thicker atmosphere like the Earth. And with time, the Martian atmosphere escaped due to all the X-ray and UV light from the sun. It can also affect surface water on these planets. It can cause the water to evaporate. So my colleagues in astrophysics tell me that entire oceans on planets can be evaporated from the emission from the parent stars. So this obviously has a big impact on the development of life elsewhere in the universe. All right, so I'll move along here. Here was kind of a cool movie. During that eclipse in 2017, some people came to talk to me about a PBS Nova TV special, and so they used some of these things that I've been saying to you guys, and they made a really slick movie, but let's go on. All right, so now let's move from these tiny nanoflares to giant coronal mass ejections. These coronal mass ejections are huge amounts of magnetic field and plasma, magnetized plasma clouds being blown off the sun, propagating through the heliosphere and impacting Earth and other planets. And these things are, well, each mass ejection is roughly 1 billion tons of material traveling at about 1 million miles per hour. So this is big time stuff. All right. Here are some great movies. I'm not playing on my machine. You know, I wonder, maybe I'll save some time at the end. I'll get out of PowerPoint and just play the movies themselves. All right. All right. The movie that didn't play showed mass ejections from a sort of a close-up on the sun, but really you can see mass ejections the best in what we call coronagraph observations. So coronagraphs are instruments that create artificial eclipses. So they typically observe invisible light. And as I said, you need to block the bright surface of the sun in order to see the corona. So in these images here, the little white circle at the center, that is where the disk of the sun would be. And then, come on, there's the disk of the sun. This bigger thing is the occulting disk. And then this is the coronal mass ejection. These are huge. Now, all right, it's working great. So here you're going to see a couple mass ejections. There's one, it's going to be followed there by another one, a big one. Well, temporarily. So here's another movie. It's playing on my machine. That's a good sign. There it is. Okay. This covers about a month of time, and there are lots of these mass ejections going off. You know, roughly one per day or so. Every so often you see this big halo come flying out, spreading out. That's from one of these things that's directed right at us. I was going to go find one, but gonna take too much time. Yeah. Okay, this is kind of neat. Good. See if you can hear this. Impressive. Let's get sound in real life. Here's the CME leaving the sun, heading to the Earth. Right there, it's hitting the Earth's magnetic field. Reconnection is happening, causing field lines to sweep back. Then there's going to be another reconnection on the back side. See it, that part. So this then leads to the aurora borealis and australis too, if you're in the southern hemisphere. Okay, let's see. So here we had the CME hitting. There was magnetic reconnection here. Field lines flip back. Then there's there it is. It's causing the aurora borealis. That reconnection on the backside of the sun energizes. They stream along the field lines, crash into the Earth's lower atmosphere, and produce the lights that are the aurora. Okay. So here's a computer simulation. I'm going to go back. All right. This is very cool. This is a real simulation showing a CME leaving the sun. All right. Propagating through the heliosphere and impacting the Earth's magnetosphere. I can see it, but there it is. So it's leaving the sun. It's propagating through the heliosphere. Looks pretty big, I guess, right? But keep watching. Hasn't gotten to the Earth yet. Now we're going to zoom in. Ah, no! It was zooming in. The Earth is this teeny tiny thing. There it. Anyway, it demonstrates the magnitude of these things. Yeah, it was just the scale. If you can see the whole movie, just the scale is just mind blowing. And they're those same processes that were in the cartoon, the animation. They're happening here in the real rigorous physical simulation. All right.
So,
So that's the University of Michigan, Gambosi and his group. Those are the Bats-R-Us code. You probably remember that code. Yeah. So CMEs cause lots of space weather as well. They can cause power blackouts. That happens when the CME interacts with the Earth's magnetosphere, causing the magnetosphere to jiggle, and jiggling magnetic fields generate electric currents. And so and these currents are in the power lines and the transformers. On the top right there, that's a fried transformer from the power grid due to a CME. The CMEs accelerate particles to very high energy. When those particles hit the electronics of spacecraft, they can do nasty things. They can cause bits to flip. So suddenly the spacecraft is doing something you don't want it to do just because the coding has changed because the particles had flipped the bits. So there have been cases of satellites being temporarily and even permanently disabled. Those same particles, they can cause damage to humans. To astronauts, so astronauts, if there's one of these energetic particle storms about to happen, they have to get in someplace safe, like get back into the space station, for example. And airline crews too. Airline crews flying polar routes. Because of the way the Earth's magnetic field is shaped, you may have noticed that in some of the things I showed. These high energy particles can get down to the lower atmosphere best around the pole region. That's why you have the aurora at the poles there. Oh shoot, I was in an auroral movie. I'll try to go back and show that. Anyway, so these particles, any one flight is just modest dosage, but if you fly back and forth, you can accumulate dosage and it can be very dangerous. And so that's a real problem. Also, you can have a problem with radio blackouts. So when there's a potential storm coming, they reroute the aircraft and it ends up flying a much longer path, and so it burns more fuel. So it's very economically troublesome for the airlines. And the communication, navigations, and surveillance and all that. Let me see. Okay, let's see this. Here's an aurora as seen from space. You've all seen aurora movies from the ground. This shows what it looks like from space. Thank you. There it is. There's the aurora. It forms this thing called the auroral oval because the reconnected field lines map into the lower atmosphere along that oval shape. All right, fine. Comment here, there are worries about a superstorm in the future. There was this huge event that happened in 1869 called the Carrington event, named after this guy Carrington. And we didn't know much about things back then. We didn't really have sensitive technologies, but still there were huge effects. Like for example, telegraph operators could operate their telegraphs and send signals even though they were not connected to batteries. Just the voltage across the lines due to the geomagnetic storm gave them the ability to send telegraph communications. And so there was a study commissioned by the National Academy of Sciences some time ago, and looking into what would happen if we had one of these superstorms sort of at the same level of the Carrington event. And it would cost billions of dollars in damage and probably millions of deaths, in fact, is what they concluded. Not necessarily direct deaths from the particles frying people, but just everything would be wiped out. The power would all be gone. We'd have shortages of everything, food in the whole bed. There'd be disease, and they just did a study and they concluded it would be just catastrophic. Okay. And so we are very interested in predicting space weather, both in the civilian sector and the military sector. There's a place called the Space Environment Center at the National Oceanographic and Atmospheric Administration. Actually, the name has changed. It's now the Space Weather Prediction Center. They do this kind of thing. At NASA, at Goddard Space Flight Center, where I work, we have something called the Community Coordinated Modeling Center, and a new program called Moon to Mars. We want to go back to the moon and then to Mars, and space weather can be really a problem. So we're working on the ability to predict space weather at those locations. All right, so we have 8 minutes left. I have kind of a fun clip from the Daily Show from many years ago I could play. But first, do you have any questions? I mean, anything that, could make more sense if I tried a second time to explain it, please.
Sam has a question.
Hello, are you familiar with
Yeah.
Mark?
Oh, sorry. Oh, sorry. Yeah, 1 second, please. We have hi. We have a question from the audience. 1 second, I'll answer that one. Then we'll get to you. Yeah, the question from the audience was the nanoflares. Do they have the same kind of effects as CMEs? Basically, no. Individually they're small, but even collectively, there's not a problem in the same way that a CME is. With a CME, you have this magnetized cloud, and it takes like 2 days for the cloud to get to the Earth and then start interacting with the magnetosphere. With nanoflares, you produce the X-ray and ultraviolet light, and that just takes a few minutes to get to the Earth. So that has effects, but it's not as immediate, dramatic. Those effects tend to show up over timescales of hours to days, but they're very important. And in fact, the military, it's funny, NASA is really interested in CMEs and geomagnetic storms. But if you talk to the military and the national security community, they're more interested in the X-ray and ultraviolet light, so the nanoflares. But so yeah. Okay, yes, please, from virtually, what was that question, please?
I'm Pamela Lewis, Solar System Ambassador for NASA, and my husband is too. We're volunteers.
Oh, great.
Are you familiar with Mark Kushner's citizen science projects that he does with the public, where the public gets involved with all sorts of projects? They take data and things like that. Maybe you can. Maybe you could hitch up with him. Yeah, go ahead.
Yeah, thanks. I know Mark by name. I've heard him give a couple talks. I'm aware of the citizen science, although not as aware perhaps as I should be. There's also someone in my division, Heliophysics, that she has a citizen science program called Aurorasaurus. But yeah, the idea is that citizens, especially citizens across the world, if you need that kind of global type coverage, can actually provide data that's useful for real cutting edge science, cutting edge research. And sometimes you can have people help you not collect data, but look at the data. You have enough eyes staring at something, they might see something that, an individual scientist would not. Although now we have AI doing that, but yeah. Yeah, so thanks. I should get more in touch with Mark and find out how we can help support his efforts.
Yeah, I mean, it's amazing of the data collection and what you do. And I think Goddard's wonderful. And I've been to Goddard a few times helping out there. But it's sad that Goddard in New York City is closed, and the administration wants to cut out 50% of science. And I just figured this might be a way of stopping it as well.
Yeah, I don't know if you heard that, but yeah, the Goddard had a satellite center in New York City, which was closed. There's a famous guy who studies climate change who works there. And so I don't know what he's going to do. I guess those people are going to maybe they're going to move down to Goddard. I don't know. To the college.
James Hansen. I met James
He's the one.
several times.
Yeah, it is.
And he's a terrific guy. And I'm from New York City, so I used to go down there a lot. It's just horrifying.
Yeah. And so the proposed budget from the administration calls for a 50% cut of NASA science. 50%. It'd be devastating. So there's not too much I'm allowed to say on these issues, but that's all in the news. And so how you choose to respond to that is up to you. George. Promises, okay. Well, with active regions, but polar crown filaments as well. Yeah. Yeah, so George was asking about solar prominences. So, hmm, mhm.
Guys here that, and they tell the concept.
Right. Yeah. Yeah. So George was asking about prominences. So for the amateurs, you've seen these a lot, right? You look at the sun in H alpha light, and you see these long snaky things. Those are called filaments when you see them against the disk. They're dark against the disk. But when you see those things at the limb of the sun, they're above the limb of the sun, and then they're called prominences, but they're the same thing. So George was pointing out that you have prominences both in active regions, but also in the quiet sun, and the fields are much stronger in active regions than the quiet sun. And does that affect the way that they form? I guess it's one of the questions, and also the suspension aspect of it too. They sit in places, like I talked before about how the magnetic field and the plasma are frozen together. So if you had, and these prominences are especially heavy gas, especially cool and especially heavy. So if you had an arching coronal loop and put a prominence in there, it would just slide down the leg of the loop, okay? So prominences are suspended for long periods of time because the magnetic field has upward concavity. It's like a dip, so it's like a hammock. So that this cold prominence material can sit inside this hammock for long periods of time. As to how they form, oh, I'd love to talk about that. There's this amazing phenomenon called thermal non-equilibrium. And I'll lose you right away, but I'm going to spend 10 seconds. So normally, if you have coronal heating, which is steady, and nanoflares are not steady, they're very bursty. But if let's suppose you had nice steady heating, just unchanging in time, then your coronal loop would get into some kind of an equilibrium, and it wouldn't be evolving. It would also be steady. But if the coronal heating, the steady coronal heating is concentrated at low altitudes, even if the heating is perfectly steady and doesn't change in time, the loop cannot find an equilibrium. It's constantly going through a cycle trying to find an equilibrium. It's not there. And during this cycle, it forms a cold blob of gas. And we believe those cold blobs of gas, which we call condensations, are sort of the building blocks of these prominences. And that can happen both in quiet sun and active regions. So. Well, that line, I think you know, that's the magnetic neutral line. So for prominences in the quiet sun, although they're long things, they're not actually tracing out field lines. Rather, the field lines are kind of going perpendicular to them. And each field line has a little blob of cold gas, and all those blobs of gas are lined up in a nice organized way. So you would think that the prominence is going along the magnetic field, but it's not. The magnetic field is kind of perpendicular to it. So it's kind of misleading in that regard. But that long line and all that organized structure, that's the places where you have strong positive magnetic field and strong negative field, and this neutral line, it's called, in between, separating the strong positive and strong negative, and the prominences lie along that neutral line. I'm sure you followed all of that 100%, didn't you? Well, it's hard to answer. The question is, how long does the CME last? Okay. So the CME goes off. It takes roughly 2 days to get to the Earth. And then, yeah, well, yeah, the reconnection, magnetic reconnection that happens that drives the aurora, yeah, that goes on for hours. Yeah. It's variable depending on the event, but yep. Right.
Is that real though?
Yeah. Not in the sort of the cartoon movie, but in the simulation that I guess didn't show up so well of the magnetic field lines, that was, oh, but that was not, yeah, I'm sorry, it was not real time, right? Time is greatly sped up. That was your question. Yeah. Time is enormously sped up. So, the hours, yeah. So when the CME hits the Earth and starts doing its stuff, that typically goes on for a few hours. Something like that. Well, they are very big, so it doesn't have to be a direct hit. It can be kind of a glancing blow. So I don't know if this is hard to answer as well. I would say maybe just throwing out some number. 10-ish% of CMEs hit the Earth's magnetosphere. 10% maybe, 20%, something like that. But the magnetic field contained within the CME has to have the right orientation. Remember I said early on, magnetic fields have direction. They have arrows attached to those field lines. And in order to have reconnection, you have to have fields that are anti-parallel. So let's say the Earth's magnetic field is pointing downward, and it is. The field comes up from the North Pole, wraps around the Earth, and goes back into the South Pole. So if the sun's over there, the CME is coming this way. The sun is here. The CME is coming this way. Here's the Earth's magnetic field pointing downward. If the CME's magnetic field is pointing downward as well, they don't interact. The field just slips around the magnetosphere. But if the CME's magnetic field is pointing upward, now they're anti-parallel and they can reconnect with each other. So that's a big part of that question. How many CMEs interact with the Earth? Sort of half as a crude number, because the magnetic field orientation is kind of random. Yeah. Yeah, but yeah, you can't. The way magnetic fields work and magnets work in a neutral gas, not a plasma, a neutral gas, is different from the way they work when the gas is ionized. So you can sometimes get useful insights by thinking about magnets in the room, but sometimes you can mislead yourself. Yeah.
Okay. Did you say, are you watching it all?
See that one, that's the one I need to see. I've got one more here. I don't want to take up too much of your time, but we're gonna go past 6.
Yeah, you ended the observatory choice.
Maybe.
Let's see it.
So there
Just maybe.
there is a question,
Okay.
are the northern lights more active when the sunspots are more active?
Yes, the northern lights are more active when there are more sunspots, because when there are more sunspots, there's more solar activity in general and more CMEs. And it's the CMEs that give rise to the northern lights. Yes. Okay, yeah. So you've been out for a little while. There's really a strong consensus, even including the wave advocates, that active regions are heated primarily by nanoflares and reconnection. Quiet sun, we don't know. Waves, reconnection, we don't know which one is more important. But active regions, it's nanoflares. Each color maker. Yes, that's a big part of it. Yeah. Not only is it stronger, but our magnetic field is this big dipole field. It's very organized. There is no large-scale dipole field on Mars. There may have been at one point, but now there are just these small crustal fields, kind of irregular, and that I think enters into that as well. Yeah, they have strong fields, as I think. I mean, it must be the case. Yeah, Mercury for sure does. Right. think Venus does.
Gas giants do too. We see auroras on the gas giants and some Jupiter. Yeah, and Uranus and Neptune.
It's my opinion, the reason why we don't have, that Mars does not have this, primarily.
Yeah.
One, the escape velocity of the gas is much lower, and also that's going to affect the geological process. Current going to affect that kind of thing. That would be my,
Well, we don't want to keep it go too late tonight. Yeah, and so thank you very much, sir, for
Yeah.
taking the time to come visit with us.
That's pleasure.
But anyway, we'll have to work through this again. But thank you much for your attention tonight. We had a number of people online as well as in person, and Rob is now here. And so please look at the stuff on the website and please volunteer. And we look forward to seeing it. And I think this worked out pretty well this time. Next time we'll be doing the same thing. We'll be starting at 4:30 and have the informal at 4, and we'll see if we get all the communications work better next time. Thank you much. Have a good evening.